Good afternoon, everyone. I'm just having a little bit of trouble getting online today. So we are going to continue what we started. So let me get your attendance today. Don't forget to put it on the chat. Please put your name in the chat for attendance. Okay. All right. All right. There's a few more right there. Okay. Okay, I'm admitting everybody. Just give me a minute. It takes a little while. I think I got everybody. But go ahead and put your name in the chat like we always do, please, for attendance purposes. Okay, so let's get started with our next part, which is what I told you was we were going to start today with somebody else is in. Okay, hold on. We're going to start with not polarity because we know how to do that, but intermolecular forces, which is a pretty simple kind of thing, and it is our next unit or topic. Intermolecular forces. So intermolecular forces are forces that happen between molecules, and they are very, how would I say, weak, basically, compared to intramolecular forces. Intramolecular forces being, okay, this is not the one I want. I want the purple one. Hold on, got the wrong PowerPoint out. Let me go back to the purple one. I like the purple one better for this. Okay, so intermolecular forces PowerPoint is the one that says van der Waals. That's the one that we want, which is van der Waals forces and intermolecular forces are pretty much one and the same. If I can find you, there you are. Okay, sorry. Sometimes it gets lost on me. Okay. Nope, that is not the one I just asked for. Okay, so it is not that one. It is the other one. Whoa. Okay. Intermolecular, where are you? Inter. There we go. That's the one I want, the purple one. Yes, that's the one. Okay. So this PowerPoint, it's called intermolecular forces, not van der Waals. The van der Waals is the one we don't want. This one, yes. All righty, now let me share my screen with you so that you can see it. All right, so for every single thing that we're going to do, we're going to have a description basically of what, or more like a list of where they apply, okay? So that'll help you figure out these really quickly. It's very easy. All right, so basically, like I said, intermolecular forces are attractive forces between molecules. What does between molecules mean? You know how some of them are charged, some of them are ionic, and some of them are nonpolar. That's not what that would be, but the ones that are polar and the ones that are ionic are going to attract each other, and that's what that's about. Okay, that's what this is all about. So when you're looking at that, you also have the other word, which is intramolecular forces, and they're different from each other. Intra means within the molecule, and within the molecule you have bonds, and that's what you're looking at. These are not bonds. These are attractive forces that happen between molecules that kind of pull them to each other. All right, so the next thing that we're looking at is how do they compare? Well, it takes 41 kilojoules to vaporize. That means to change it from a liquid to a gas, right? 1 mole of water. But it takes 930 kilojoules to break all the oxygen-hydrogen bonds in 1 mole of water. So the top is intermolecular forces, so boiling point, melting point, heat of vaporization, all of these things are intermolecular. Intramolecular, like I said, are the bonds. So intermolecular forces are much weaker than intramolecular forces. And this is how we measure them. Like I said, heat of vaporization, heat of fusion, heat of sublimation, there's such a thing. All right, they're feeble, like we said, but without them, we would not have the proteins. Like, well, this one on the right is showing you that's a protein with a helical structure. And that helix happens because of the way the amino acids interact with each other. Okay, so that's one of the reasons why this is very important. The other thing, DNA also turns the way it does because of this. And when we are replicating DNA, it's easy to break the bonds because they are not really true bonds. They are actually the attraction between the nitrogenous bases, which is what makes the rungs, right, in the ladder. All right, that is what is known as intermolecular forces. It's usually hydrogen bonding that happens there. All right, so these are the 4 types that we're going to look at today. London dispersion forces, dipole-dipole interactions, ion-dipole interactions, and hydrogen bonding. So let's look at London first. In order for London dispersion forces to occur, all you have to have is an electron cloud. So guess what? It happens with both polar and nonpolar. Mainly nonpolar. You know, that's the only force in a nonpolar molecule. So you got that? The only force in a nonpolar molecule. Make sure you write your name on the chat, please, so we have attendance that way. It's only 9 and there's 13 of you in here. So I need more. Anyway, so the other thing that you need to know is that the larger the molecule or the cloud, the larger the dispersion forces are. So compared to fluorine, which is above, see, this is where all that periodicity comes in. Compared to fluorine, which is smaller, iodine, which is much bigger, would have greater dispersion forces because it's easier to distort its electron cloud. And basically, like I said, it happens because electrons are negative. And if you put another electron next to it, it's going to shift over away from it because it's called repulsion. And that's what that is. Okay. And the other thing is in hydrocarbons, this is something that'll be useful for you when you do organic chemistry. In hydrocarbons, the boiling point of alkanes will increase with the length of the carbon chain. So long chain alkanes have larger dispersion forces, so larger boiling points, melting points, whatever, than shorter ones, okay, because they're easily polarizable. All right, so if you look at also another thing that matches with this is molar mass. And molar mass is basically just how much something weighs per mole. So if you have a greater number of electrons, we said, if we have a more diffuse electron cloud, which means bigger, then you will also increase. But molar mass will definitely be another factor that you need to look at. Hydrogen is only 1.01. Fluorine is 19 point something. What is your mass? Fluorine is 19 even. Okay. Chlorine is 35.45. Bromine is 79.9. And iodide is 126.8. So when you're looking at that, the molar mass is increasing as you're going down. And look at the melting points, it's also increasing. Right, so that's another factor that you have to remember. Okay, so let's keep going. All right, so basically, how do we know when something is polar? Well, we know this already, but why is it polar? We may not know. Okay, so a dipole is what it's known. It's because there's a interaction between the positive dipole and the negative dipole of a molecule. Okay, so if you have any lone pair electrons in the central atom, you are going to be a polar molecule. And also, if one of your atoms is different from the rest, or two of them, it doesn't matter. If you don't have the same atoms all the way through, then they are going to be different also. You're going to have a polarity going on. Like right here, all of the hydrogens are hydrogen, all of the carbon bonds are hydrogens, therefore they all cancel. See, they actually cancel out, just like the carbon dioxide here cancels out. So therefore there is no dipole. All right, so they are attractive forces between polar molecules, and it helps them orient themselves in a solid. All right, so positive with negative and negative with positive and so on. So if you were to look at these two, you can see that you have a different, remember what I said, one of them is not like the others. Okay, so there's a different one bonded to that central carbon. That, oh, let me get the spotlight, which I'm not spotlighting, so you don't know what I'm pointing to. This central carbon right here. This central carbon right here. This is totally different. These are the same. These are methyl groups. So these methyl groups are identical. Therefore, this is nonpolar, but this one's polar. And that polarity is caused because oxygen is more polar, more electronegative than carbon. And so it would do what is known as a negative dipole, as in it would pull towards itself, making a negative charge, a partial negative charge, and the carbon a partial positive. All right, let's keep going. Okay, so also ion dipole is the attractive forces between a polar molecule and an ionic compound. Remember, ionic compounds dissociate in water or in any polar solution to form ions. And those ions get attracted by the positive and negative ends of those molecules. And you notice what it says here, the larger the charge, the stronger the force. So if you have a large charge, then you have much more attraction, right? Okay. All right, so let's keep going. This is the dissolution, or the solvation, I should say, of salt in water. So it's called actually hydration in this case, because it's a solution made with water. So this is what happens. Hydrogen is positive, so it attracts the negative chloride ion. Oxygen is negative, therefore it attracts the sodium ion. And vice versa, right? So this is what it all boils down to. So always remember, like attracts like. So if polar molecule is put in a polar environment, they're going to attract, they're going to dissolve. But a polar one put in a non-polar one solution is, not solution, solute, is not going to dissolve. Like oil and water don't mix. Why? Because water is polar, oil is non-polar. All right, and here's the last one. And this is the most important and the one that really causes the most intermolecular force. And it's also the largest one of all, the strongest. Okay, so it is a special dipole-dipole interaction that happens between the hydrogen in a polar molecule. It has to be polar now, and an electronegative oxygen, nitrogen, or fluoride ion, or fluorine ion, sorry, atom in the any molecule. So there have to be, notice this dipole-dipole, that means they both have to be polar, otherwise it will not happen. Okay, so if you had NH4, that would not happen because there's no polarity. Okay, so remember, carbon, no, not carbon, sorry, oxygen, nitrogen, and fluorine only. Okay, so, and it is symbolized by dots. Look over here. You see these dots? That's the actual hydrogen bonding that's happening between water to water molecules. That's why water has so many different properties, and we're going to talk about those in a minute. Okay, so these are the four forces. Now, let's summarize something here, and we're going to see how it works. So I'm going to put them in white since everything else is in white, and I'm going to type. Well, maybe black. Let's make it black, because typing in white is not going to be able to see it, what I'm typing. Okay, these happen, oops, I said black. Click black, but it didn't. There. In all molecules. That means polar and non-polar. Okay, so that's that. Molecules. Molecules. Okay, so that's everywhere. Okay, so if you see London dispersion and there's a molecule, they all have it. Dipole-dipole interactions happen only between polar molecules. Type today. Okay, ion-dipole interaction happen only between polar molecules. And ions, or in this case, ionic compounds, right? Compounds. Okay, where's my O? There. And hydrogen bonding is very special. Happen between polar molecules containing hydrogen and another, okay, a polar molecule containing hydrogen and another polar molecule containing either fluoride, oxygen, or nitrogen. Okay, either. I said either, I didn't put either. Okay, there you go. So those are your summary. So when we are looking at these, remember how we said we were going to look at them later on? And this one is, let me, well, I can't move it anymore. I don't think. I I cannot. Okay. So anyway, so that's how it works. These are your main 4 forces that you will see. Now, water is a very special type of molecule. And it is one of the most polar, and there are some properties that arise because of it. And we're going to go look at those real quick. And let's see, escape this. It won't let me escape it. Why? There we go. All right. So close that. And there it is. No, that's liquids and solids. I don't want that one either. I want water. This is the one that came up and I didn't want. All right, so this is not you. Nope. Okay, there we go. Now let me go back and look at properties of water. And there is a PowerPoint called Properties of Water. And let's see, where are you? Where are you? There it is, right there. Now it disappeared again. I hate when that happens. There it is. Okay, so properties of water. Oh, and we're gonna get these things taken care of to clear all those joints. All right. All right, let's go. Let's download you. I think I got you. There it goes. It's downloading. All right, so we're going to open that and start looking at it when it opens. Right. Okay, so we are looking at a particular PowerPoint that I created a while back. It's actually a biology one when I used to do AP Bio, but it says, should we control a chemical that causes excessive sweating and vomiting, is a major component in acid rain, can cause severe burns in its gaseous state? It sounds horrible, doesn't it? Accidental inhalation of it can kill you. It contributes to erosion, decreases the effectiveness of car brakes, and has been found in tumors of terminally ill cancer patients. Okay, so what is this chemical? Well, the actual name is dihydrogen monoxide, and it is also known as water. So yes, water can do all of that, but if you think about it, it is just a funny thing. Okay, so we have a question. What is the molecule that is the most common in living cells? Again, water. Why is it water? Because everything is made of water. 70 to 95% water, depending on the type of cell you have. Look at our planet. What do you see most? Water. It's called the water planet. The reason that is because we have certain properties, don't worry about that, known as cohesion and adhesion. And do you know like in Louisiana, we have a lot of what they call wetlands. And the reason they are good is because the polarity of water results in hydrogen bonding with other water molecules, which prevent flooding, especially if it's already wet, because water is attracting water. So liquid water is also adhesive. What does that mean? It sticks to other kinds of molecules, again, due to hydrogen bonding. This is one of the reasons right here that trees can transfer water all the way from the roots way down below to the leaves way up there. It's because of cohesion and adhesion. Both of those, right? Another one is surface tension, very high surface tension. If you've ever belly flopped into a pool, you know how high that surface tension is because it hurts, doesn't it? All right, well, this little guy can walk on water because of its surface tension and also because it has certain light features of its body plus long legs, but we couldn't do it. The surface of water is difficult to stretch or break. Again, hydrogen bonding. Water also has a high specific heat. That is the amount of heat needed to raise 1 gram of water 1 degree Celsius. Why? Again, hydrogen bonding. Water acts like a large molecule, but it's small because it bonds to itself. All right? So remember, we looked at these already, but we're not going to look at those. Okay, so the other thing is water stabilizes temperature. How does it do that? Because it can absorb and store huge amounts of heat from the sun. Therefore, climate is moderated and we can live on the surface of Earth. Otherwise, we could not. This is why Venus can't be inhabitable, neither can Mars. All right. Another thing is it has a high heat of vaporization. Again, all it is the amount of heat required for 1 gram of a liquid to convert into a gas, okay? And another thing, have you ever noticed that when you sweat, you cool down? That's why, because as you sweat, you put out that water, right? That water actually absorbs your skin temperature and it evaporates, and that's why. Okay. Again, hydrogen bonding. Another thing, I don't know if you've ever noticed, but when you put ice in water, it floats. And that's weird because all solids are more dense than their liquids, except for water, because of hydrogen bonding. And this is the reason. Once the hydrogen bonds are frozen, they are fixed in positions and their distance is higher than those of liquid water. So it floats. Normally, though, this is the truth right here. Benzene, for example, frozen benzene sinks in normal benzene, but water doesn't. That is called as a density anomaly of water. It's another property. Think about it. If all organisms that live in ponds in the winter would die every time the water, the temperature drops because water started freezing from the bottom up, they would all die. But instead it floats, so it freezes from the top down. Therefore, little guys can still live. You see that? Isn't that cool? Very well designed. All right. And another thing, it's a very good solvent because water will dissolve pretty much anything that is polar. And there are many more polar substances and ionic compounds than there are nonpolar. Okay, and that we already know these words. Okay, and that's just hydrophilic materials. Those are the ones that dissolve in water. Hydro means water, philic means loving. So they are polar. And hydrophobic materials are nonpolar. Hydro meaning water and phobic meaning fearing. So water fearing, they don't like water. Okay. And that's it. That's all we need. All right. So as you see, water is a very versatile thing. Okay. And we need it to survive. Without it, water, we wouldn't survive at all. All right. So let's close that and finish sharing this one. I think this is the one I want to, yeah. Okay, so I'm going to go back and look at our table that we were doing. And I think I have it right here. 2, 4, 2, 4, somewhere in here. Sorry, I had it open, but I had to log in so many times. Nope, that it didn't actually want to work. So no, this is definitely not you. No, save it. Go away. That is not you. Okay. Let me see. I gotta find it. Sorry. Okay, I am looking for it and then I'll share my screen because it'll take me a little bit. All right, it's called Vesper Lab. So VSEPR. There it is. Aha, found it. Okay. All right, here we go. Now I can go ahead and share with you. Now that I found it. Didn't want you to sit there and watch me search for it. Okay, so let's share now. All right. So remember, I told you I was going to finish it, and I did. The one thing we didn't finish, and we're going to finish now, is the other part. Well, these I couldn't do the Lewis structures, but the intermolecular forces. Okay, so if the word is nonpolar, what did I tell you? Who is the only intermolecular force that we can have here? The answer is, oops, hold on. Did I have it so that I can? Yep, I do. Okay. It didn't look like I could, but I guess I can. Okay, so here, I don't know why it's not letting me. Ah, there it is. London dispersion forces. The only one that nonpolar molecules can have, unless they're charged. And that's the main thing. We want to look at, see if they're charged to begin with, right? And they're not. None of these first ones are charged except for the second one. So let's just, for the last one. So let's just go ahead and click it up so we can look at it. Okay, there we go. So all of these are going to be London dispersion force, all of these, because they are nonpolar. London dispersion force, London dispersion force. And then this one right here, it says polar. So polar is going to be dipole, dipole, right? And it is also charged. So it is possible it can do an ion dipole when it dissociates. So there you go. Those are the forces for this one. Okay. These are these, they're in that order. So I showed you. Okay, the next ones are water, sulfate, ion. This is known as another type of ion, but we don't. And this is phosphate ion and NO3, which is nitrate ion, and NO2 positive. Okay, so polarity, again, we said that was water. So water has everything except one. Okay, so it does London dispersion because everybody does that. So you might as well just put it all the way down. It does have dipole, remember, because it can induce one. And it also has hydrogen bonding because water is hydrogen and it also has oxygen and they can do them, attract each other. All right, nonpolar London dispersion force. But this is a charged molecule, therefore ion dipole. And I'm just putting the initials because it would take me forever to write all this. London dispersion force, and we have charge. Therefore, we can do an ion dipole also. Okay, this one, charge also, and is nonpolar, London dispersion. And when it dissociates, ion dipole. And then this last one is also charged. So, and it is polar. So we got a lot of stuff that it can do. Oh, sorry, nonpolar. So London dispersion force and ion dipole. When they have those characteristics, there's only one that has all the forces, and it's not water. Okay, so we got carbonate ion, which is charged, and then the rest are, then there's nitrite ion also. Okay, so carbonate ion, not charged, therefore, not polar, therefore it is London and ion dipole. This one is polar, so we also have London always. Remember that. Dipole, dipole. Now, let's look at what kind. Nope, nothing there has hydrogen, so it can't have hydrogen bonding. Can it induce ion dipole? Nope, it's not charged. Okay, next one, NO2 negative. So this one is got London dispersion forces. It has dipole, dipole. And it can also induce ion dipole because it does have ionic qualities. All right. not hydrogen bonding because it doesn't have hydrogen. The next one is PF3. You notice it's polar. So London dispersion and just dipole-dipole, not charged at all. Yeah. Okay, so this is nonpolar and it is Si. Okay, this is just London dispersion. It doesn't have anything else. It's not charged. It doesn't have anything. See, nothing but that. All right, the next one is ammonia. Okay, ammonia is polar. And since it is polar and it has hydrogen, London dispersion forces, ion dipole. No ion dipole, sorry, this is not charged. Dipole, I meant to say, and hydrogen bonding. Okay. The next one is, this is the one. This is the hydronium ion. It has London dispersion. It has dipole. It has hydrogen bonding. Oops, sorry. It has ion dipole because it is charged. So it can induce a dipole with another one. And it also has hydrogen bonding. This is the only one out of the ones we have that has all four. Could have all four. Doesn't have them, but it could have them. Okay. This one is nonpolar, but it is charged. So London dispersion forces and ion dipole. See how easy it is to figure these out once you know if it's polar or nonpolar? Polar. So again, London dispersion, dipole. And it is charged, last I saw. See? So that means ion dipole also. And the last one is the one that is, one is not like the other. So it is polar, but it's not charged or anything else. So it's just London dispersion and dipole. And that's it. That's all of them. So now you see how all of the Lewis structure is the most important thing you can do over here. So because the Lewis structure, if it's correct, is going to give you all this information, every bit of this. So you want to go ahead and know it, know how to do it really well. All right, so that's basically everything for today. We finished all of the stuff. Did I skip one? No, I didn't, did I? No. Okay, so we finished all of the stuff that we had to do, that which was the intermolecular forces and the properties of water, which is part of that. So if you look at, and I'm gonna go stop over here, hold on. Where am I doing? Must stop here. Hold on. I'm trying to stop the share. There we go. I couldn't see it because things get under. All right, now I want to share again, but this time we're going to just go to the modules again, and I want to see that we are ready for another test. Already, you could be taking test 3 already took, test 4 you should have already taken, and this is test 5. Okay, except for one thing, molar mass. So molar mass calculations, I kind of showed you last time. So for molar mass calculations, basically what you do is you just add whatever is there. So let's say let me just share you a real quick one. We're doing a very complicated one, and you'll see how easy it is to do. All right, so I'm going to share my screen with you, but this time it's not my screen. This time I'm going to share the Blackboard. Okay, so let's say we have this molecule to do. So let's say it's nickel 2 sulfate hexahydrate, no, nickel 3, let's say 3. Okay, so sulfate hexahydrate. So it'd be all this mess, I know. That way you will not have any doubts of what we're doing. Okay, so how do we do this molar mass? Well, we look in the periodic table. And based on these subscripts right here, it's telling us how many of them we have. So you do 2 times, and nickel is on here at 58.69. Let's see, 69 or yeah, 58.69, 58.69. And that's it. So basically we are doing here 58.69 and then plus our next one would be sulfur, and there are 3 sulfurs times 1, right? So that is 3 times, and sulfur on the periodic table is 32.07. Then we got plus 4 times 3 is 12, so 12 oxygens at 16 each. Plus, I know I'm still going. Then you have 6 waters. You can do this as separate, and that's usually what they want you to do because these are used for hydrates. And you do 6 times, and water is actually 2, it's 1.01 times 2 plus 16, so it's 18.02. And that gives you the water. And all of this added together, just like I put, gives you the molar mass. And that's it. That's how you do molar mass. It's pretty simple. And remember, this number right here in front means that you're multiplying all of that, right? In the hydrate. That's why I gave you everything that I could all at once. Okay, so in this case, it's going to be 2 times 58.69. Close the parentheses, plus open a new parentheses. 3 times 32, close that one, plus open a new one. 32.07. Oops, I missed the 0.07. 0.07. You want to be as exact, so don't just put 32. And then plus 12 times 16.00, so that's that one. Plus, and we have 6 waters, so 6 times 18.02, close it equals. Okay, so the molar mass of nickel 2 sulfate, 3 sulfate, sorry, hexahydrate, it is 513.17 moles. Oh, sorry, grams per mole. Grams per mole. That's why it's called molar mass. Okay, and that's it. That's how you do it. Oh, sorry, that was 71, not 17. 71. I was looking fast and I didn't see that. Okay, 71 grams per mole. So that's how you would do it. It's pretty simple to do molar mass. Just gotta watch these guys, right? The subscripts and where they are positioned. And then you just multiply everything. All right, that's that. Okay, guys, I will talk to you again Wednesday. Take care.